Hey everybody, today we're going to look at what's known as Le Chatelier's principle. Henri Le Chatelier was a French chemist who came up with this process or this principle that talks about how we can manipulate equilibrium systems. So when a system goes to equilibrium, the reaction seems to stop and no longer work, but don't forget that the reaction is constantly in this dynamic equilibrium, meaning that it's constantly producing products and constantly reacting back and producing the original reactants. But what Henri Le Chatelier found is that there's ways of manipulating those equilibrium systems. So if we're not getting a lot of products, we can do something to try to get more products. So let me show you what he did. His principle is this: if we change an equilibrium system, so if we do something, so we let the system get to equilibrium and then we change it. We do something, we add something to it, we change the pressure, we change the temperature. What's going to happen is a system that was originally at equilibrium is no longer going to be at equilibrium because we just disturbed it, we changed it. What happens is the reaction always shifts in a way to reduce that change or effect that we did. In a sense, the reaction is always going to go back to a new equilibrium. Okay, so equilibrium is always achieved in all chemical reactions, and this is going to happen when we make these changes. So I'll explain a little bit more in more detail, but the idea is whatever we do, the reaction will respond by undoing what we did in a sense. Okay, so we were going to look at three different ways or three different changes that we're going to invoke in the system. We're going to change the concentrations, we're going to change the pressure and volume. Don't forget that Boyle's law, pressure and volume changes go hand in hand. So if I change the volume, I'm going to be changing the pressure. And then we're also going to look at temperature changes. Okay, so we'll look at these one at a time. So let me show you a little video and try to talk you through the concentration change. Okay, what I have here is a chemical reaction. This is a simulator of the chemical reaction of the substance A reacting with this thing BC. And what's happening is it's going to form the products here. So that's our general chemical reaction. So what I'm starting with is 50 molecules of A and 50 molecules of BC. And they're both put into the container. So I start out with my reactants. Now I'm going to start the experiment, and what's going to happen is these two are going to react together, A and B, and start to produce my products. So the reaction initially shifts to the right. So according to Le Chatelier, since I have more reactants than I do products, the reaction has to shift towards the products to start off with. All right, now let the system go. Products are forming, and eventually what I'm going to do is I'm going to reach equilibrium. So it's going to look like the products stop forming. So I'm at about 9 or 10. That's probably better to look up here at the chart. You can kind of see that the bars are a little bit easier to watch. Okay, so they're about 10, 11, somewhere in that area, 12 depending on what you're looking at. But again, it looks like the reaction stops. Okay, so at this point I'm favoring the reactants. I'm not getting very many products out of the system at this particular equilibrium. So what we want to do is we want to find a way to produce more products. So Le Chatelier found that if I come over here and I change one of the concentrations, I could change any one of the four I want. What if I increased the concentration of BC and made it go up? What's going to happen to the reaction? It's going to respond by doing something. So I increase the concentration of one of the reactants. Watch what happens to the reaction as we kind of let it go for a few minutes here. Notice that these are going to start to go up. Now we're up at 15, 16. So what we're doing is by putting in more reactants, I increase the amount of reactants. There's more reactants to react with A, and therefore to produce more products. What I'm doing is I'm shifting the reaction towards the product side. K is going to still be the same thing. I still favor the reactants in this reaction. It's just that now I have more products as a result. So even because I have more of the reactants. So I have to get back to that equilibrium position. So the reaction will respond by reacting more with the reactants to produce more products. And notice now I went from 11 to 12 to now having 21. So I can increase the products. Now what would happen if I come over here and I take out some of AB? If I just remove it completely from the system. Watch what happens to the amount of C. Maybe not working as dramatically as I had hoped, but maybe I need a little more of the A to react with it. Okay, maybe I'll not do that part. There we go. Okay, so you just need a little bit more time to react. So you can start to see that I'm starting to build up more of the products. So just need a little bit more time to react. There's a lot of particles in there. Temperature's kind of low, and we're going to talk about temperature effects. But by removing one of the products, the reaction responds by replacing one of those products back into the system. And that's essentially how concentration affects. Let me try this one more time here. Let the reaction go back to equilibrium. Okay, so about 9, 10, 11. So let's go ahead and take out C completely. When we do that, the reaction responds by shifting further to the right to bring in more C, and as a result, what it does is it increases the amount of AB. So the reaction is shifting to the right. So if I remove a reactant or a product, it responds by reproducing it in the reaction. Okay? So what we saw was that at equilibrium, the concentrations are constant. So we'd establish equilibrium. I changed one of the concentrations and disturbed that equilibrium, and as a result, the reaction responded by taking away what I added or by adding what I took away. So if I add something, the reaction shifts to remove it. If I remove something, the reaction responds to take it, and add it back in there. So if I add a reactant, it's going to shift to the left, towards the products to use and consume that amount of reactant that's in there. Okay. If I add more product, then it's going to take that product and shift it more towards the reactant side. It always responds by moving away from what I add. Okay, so that would be concentrations effect. And I'll show you an example of that in class as well. All right, so let's take a look at the next effect, which would be pressure volume. Okay, what I have here is a chemical reaction that's just basically what's happening is iodine is breaking down from I2 to individual iodine atoms. Okay, so we got the iodine molecule breaking up into iodine atoms. And that's the reactions going on. And if we look at the equilibrium, again, just like we saw before, we got the reaction going on. Iodine is lower in concentration than the individual atoms. So therefore, I'm favoring the products this time. So K would be greater than 1 for this particular reaction. Now what I'm going to do is I'm going to change the volume, and as I change the volume, I'm going to change the pressure, because as the volume gets smaller, the pressure is going to go up. So I'm going to change and increase pressure. We're going to see what happens to this reaction as a result of increasing pressure. So at increased pressure, my volume gets smaller. So now the reaction has smaller space to move around in, and as a result, the reaction is now going to change and shift and go into a particular direction. So as these start to collide and react more, we're going to change. And notice what happened is we now have more I2, and the gas becomes more and more dark purple as the purple molecule starts to form. Now why is that happening? Well, if you notice here, I have 2 molecules of iodide. Over here, I have 1 molecule of iodine in a molecule form. So individual atoms, 2 of them, take up more space than the 1 individual molecule. So if my volume gets smaller, I don't have as much space to move in. I have to shift to the side with the smallest number of moles. Remember with pressure and volume that they're connected to moles. If I have a larger number of moles, then I would need a larger volume to make space for that. So what we find is that if you decrease the volume, the reaction will shift in the direction that will go to the smaller number of moles. All right, let's try looking at one more example. If I decrease the pressure, make the pressure bigger, we should see the opposite happen. We should see it shift more towards the iodine because there's more space now, and I can shift and I can produce more of these individual molecules, the individual atoms that can now move around and fill in that space. Okay, so let's give it a second here and it will show me the reaction. It will now shift and change. This will go up and this should go down according to my prediction here. And as you can see, iodine now goes up. Why? Because there's more space. Notice the color becomes more pale because we now have some of the white molecules, white atoms as opposed to the purple molecules. Alright, so let's recap that in the notes. Okay, pressure and volume changes can be very confusing, so you gotta be patient with these. I know this is the hardest part for students with a Chatelier's principle. So the way I do this is I always focus on the volume. Always focus on volume. If the pressure goes up, then my volume goes down. If my pressure goes down, volume goes up according to Boyle's law. So keep that in mind. They're inversely proportional. Here we're keeping temperature constant, and this is only true for gases. So you can only use gas equilibrium. So solids, liquids obviously don't have an effect anyway, but aqueous systems are not affected by pressure volume changes. Okay, because they're all done underwater. So as we saw in the video, if the volume is changing, we're going from a large space down to a small space. Well, I can't fit as many gas particles in a smaller space, right? Because the smaller space now has less room to move in. So if I look at volume, nRT over the pressure, well, we've changed the pressure, so now we have to look at how the volume is going to respond. It's going to be based on the number of moles, because the lower the number of moles, the less space it's going to take up. Obviously, moles are the number of gas particles. The more gas particles, the larger the volume. So they're proportional to each other. So if the volume holding the gas is reduced, the response of the system is to reduce its own volume. How does it do that? By shifting to the side of the reaction that has a smaller number of moles of gas, by the way. All right, so let's take a look at some examples here. All right, so I have in this reaction, I have dinitrogen tetroxide and nitrogen dioxide. All right, so obviously this is producing 2 moles of gas. So I get 2 of these nitrogen dioxide molecules in the container, which are going to take up more space than 2 of these compounds here that have oxygen and oxygen and an oxygen. It's a bigger molecule I'll give you, but it's still 1 molecule versus 2. So if my volume, okay, the container is reduced, I have a large volume, and now I have a small volume, I have to make the number of moles get smaller. So how will the reaction respond to a smaller volume? It's going to shift it towards the reactant side. So I'm going to see more of this gas form and less of this gas form because the volume is getting smaller. Volume is going down, so we have a smaller volume, less space to move around in. I need to shift to the side that has, every time the reaction shifts in this direction, I take 2 molecules and I make 1. 2 molecules become 1. So I'm going to be taking up less space if I shift more towards the dinitrogen tetroxide. Okay? All right, let's try looking at another one. Here I have nitrogen, hydrogen, and ammonia. I'm not going to draw out the molecules. You can kind of picture what's going on here. But look at this side here. I have 4 moles of gas. 4 moles of gas. Notice gas, gas, and gas. Over here I have 2 moles of gas. Okay, so 2 moles. So if I shift towards the reactant side, towards the product side, if I go in this direction, I'm going to cut my number of moles in half. The volume will cut in half every time. If I shift in this direction, well then I double the number of moles, so the volume is going to get bigger. So if my pressure is going up, my volume has to be going down, so therefore I have to shift to the side with the lower number of gas moles. So this reaction will shift to the right. Okay, just to recap what a shift means it's going to react. So it's going to react in the right direction. It's going to produce more ammonia. These 2 molecules, or in this case 3 of the hydrogens and 1 of the nitrogens, are going to react together to produce 2 moles of ammonia. And every time it does that, it cuts the volume in half because the number of moles of gas are cut in half. So when we say shifting, it looks like a chemical reaction is happening. Something is going on in the reaction chamber. And then it'll go back to equilibrium and it'll look like to us nothing is happening. All right, let's take a look at one more for the volume pressure changes. All right, so here we've got hydrogen reacting with iodine to produce hydrogen iodide. All right, so I got 2 moles of gas on this side, and over here I have 2 moles of gas. So the number of moles on both sides are the same. So what's going to happen if I change the pressure? Well, if pressure goes down, volume goes up, and we have to shift to the side with the smaller number of moles. Well, they're both the same. So we will have no shift. There's going to be no change to this reaction. I can't get any more products or reactants out of this reaction. It's pretty much going to stay the same. So pressure and volume has no effect. Now, if I make one small change here, if I change this to a solid, now that's going to have an effect. So you got to watch the states of matter on these. Because if this is a solid, then I don't have 2 moles anymore. I have 1 mole. And now as a result of that, the reaction will shift to the side that has a larger volume. So in this case, well, that looks bad. I should probably put the T in there. So it's going to shift to the right. And it's going to produce more products because of the fact that we now have a larger volume, so it shifts right. Okay? So keep in mind, watch for the solid liquid gas thing. All right, one last thing we're going to look at, which is temperature effects. All right, temperature effects are going to be treated just like we would concentrations. Okay, so really, first thing we need to understand is whether it's exo or endothermic. So remember in the thermochem chapter, endothermic means heat is added to the reactants. Heat is added to the chemical reaction. As exothermic, heat is a product. So it's really important when we're dealing with temperature changes that we know whether we have an endothermic or an exothermic process. Okay, so if temperature's changed, if we increase temperature, what we are doing is we're adding heat. Because you want temperature to go up, you have to add heat. So if I add heat, what's that heat doing? Well, if it's endothermic, the heat is used to react the reactants, to make the reactants break down into products. So in a sense, I'm increasing the heat, causing the reaction to shift in this direction. Now, if it's exothermic, I get the opposite process because that heat is causing the products to react more, and therefore we'll shift the reaction in this direction. So adding heat to an exothermic reaction will shift it to the left, make us produce more reactants, while if it's endothermic, it's going to shift it towards the product side. So it's just like, you could think of this just like another reacting material. Okay, so let's take a look at an example. So if I look at hydrogen and my iodine reacting with the hydrogen iodide, this is an exothermic reaction. So I will have to tell you that, whether it's exothermic or endothermic, based on the data given. All right, so exothermic reaction, if you increase temperature, increasing temperature means that we are adding heat. Heat is going up. So more heat means that these particles, the heat is going to cause this to react and break down more. It's going to cause the reaction to shift towards the reactant. So we're going to have more reactants as a result. More hydrogen and iodide are going to form, and the hydrogen iodide is going to go away. So it's going to shift it in this direction. All right. Let's take a look at one last example. And if temperature change, what I'm talking about. Since heat is a product, we're going to treat it like a physical substance. Extra energy can be used to shift through. Okay, so I already said that. All right, one last one. Should we increase or decrease temperature to increase the yield of products? We want to make this go up. We want more products in a reaction. All right, so should I make the heat go up or should I make the heat go down? Well, if I want more of this, I want these two to react more. Well, when they react, they need heat in order to react. So therefore, I want to increase the heat, because if I increase heat, these will react more often, shifting in this direction, producing more of the product. Okay, so I know it's a lot, but we'll look at it in class, and I'll talk a little bit more about Le Chatelier. I'll show you some examples, some demonstrations in class on this, and we'll take it from there, guys. I'll see you later.